Hello students, welcome to the course on Principles and Chemical Applications of Thermodynamics. In this course, we are going to learn several important topics in the principles of thermodynamics. Now, the first thing that we are going to learn here is as follows. We are going to learn the essential concepts and the definitions which make up the basis of thermodynamics. And in this connection, we are going to talk in terms of a lot of experimental data which gave rise to the ideas of heat, work, and energy. And these ideas have been consolidated in terms of what is known as the first and the second laws of thermodynamics. Once we know these laws of thermodynamics, we are going to move over and learn the concept of entropy. And once we know the concept of entropy, we are going to combine the ideas of energy and entropy and learn about what are known as free energies. There are two types of free energies that we come across in thermodynamics. The first one is Helmholtz free energy and the second one is Gibbs free energy. And together, all these concepts make up the basic formalism of thermodynamics. We will next talk about the application of these concepts in systems of interest primarily to chemists, physicists, and material scientists. If time permits, we will also see some applications in biological systems. But primarily, our focus would be on understanding the equilibrium conditions for closed systems. And what I mean by closed systems is these systems cannot allow any change in the number of particles. The total number of particles in such system will always remain constant. In this connection, we will also learn what are known as the Maxwell's relations. Now, once we are done with the closed systems where the total number of particles is a constant, then we are going to move on to what are known as open systems. So, an open system is a system where the total number of particles can change. We will see practical examples of how these numbers can change and what is the concept of chemical potential and why this concept of chemical potential is so important in defining the equilibrium condition and the flow of matter in open systems. And finally, we are going to look at phase and reaction equilibria and electrochemical equilibrium and the application of these concepts, as I have already told you about, in a wide variety of systems with primary emphasis on chemical applications, and then we would also talk about physical and biological systems. Let us next look at what I am going to suggest as a primary reading material. I am going to suggest the textbook of Physical Chemistry by P.W. Atkins. There are several editions available. I have written down 8th or 9th edition. You can use the latest editions as well. And there are several reference books which are excellent undergraduate texts, and you can also supplement your reading material with these. And these are the 4 titles that I have highlighted here. And I would also like to point out this classic text in thermodynamics, which are generally not used to teach thermodynamics to the students of chemistry. However, many of us who practice thermodynamics in chemical systems have learned the principles of thermodynamics from this classic text by Szymanski. So I would ask you to have a look at this classic text and clarify the foundations of thermodynamics from it. Next, I would also like to highlight one more physical chemistry book which has a volume on thermodynamics, and that is a book by H. Matthew. If anybody is thinking about reading a very easy and nicely flowing text, please have a look at the book by Horia Matthew, Physical Chemistry, and the volume on thermodynamics. Of course, there are many other books available in the market. You just have to find out the book you like, the book that tells you what you want to know. Therefore, although I have suggested a list of books here, you are free to choose the book that suits you most. Now, let me start by a review of the essential concepts and definitions. This is an undergraduate course, so it is assumed that the very basic definitions and concepts of thermodynamics have already been introduced to you in your high school days. So let us see what these basic definitions and concepts are, which I expect you to know or remember from your high school textbook. The first thing is, why study thermodynamics? The primary goal of thermodynamics is determination of the equilibrium state that eventually results when the system of interest undergoes a change in state. And the next point is even more related to the practical application of thermodynamics, and that says how and to what extent we can harvest energy from different sources. So if you look back at your experience with the real world, we understand that although we can walk, we can run, we can stand, we can sit, we can sleep, we can dance, we can do many physical activities, we can sing, we can read, we can talk, but there are certain things that we cannot do. For example, we cannot fly. We cannot fly like birds. We cannot lift a load which is probably 1,000 metric ton. That is beyond the capacity of our own body. But does it mean that we are not flying these days? Does it mean that we are not lifting very heavy loads from one place and taking it to some other place? Yes, we do. So how do we do it? We do it by recruiting some other system and use its capability to do work, to perform tasks that we cannot do ourselves. And in order to do that, we need to understand that if I am recruiting a machine today and putting it in action to do some useful work on my behalf, then how do I do it? And if I have to run the machine, I'll have to give some input of energy. So to what extent this input energy will be converted to doing external work? And thermodynamics is the formal language to understand this very important question in our daily life. And in order to do this, thermodynamics had to introduce certain basic formalism and had to address one basic question. It had to define what a system is. It had to define what an equilibrium state is for this system. It had to understand that we can harvest energy only when the system passes from one equilibrium state to another. And therefore, we needed to understand what will be the new equilibrium state if we start from one equilibrium state, then induce it to undergo a change in state in such a way that we can harvest maximum energy from the system to do some useful external work. So that is the reason why thermodynamics is studied not only by chemists, physicists, or material scientists. It is studied by engineers, and they are the ones who make the machines work in an optimum fashion. Now let us move then to the concept of harnessing the energy. If I have to make a machine do my external work, I have to give some energy to the machine to do this work. So where do I get the energy from? There are many alternative sources of energy all around us. For example, the biggest source of energy is our sun. And we can use solar energy to the best of our capability if only we had the best machine to do that. These days, we have a lot of devices employing solar power to convert into some useful form of energy by which I can drive useful machines. We also know that plants use solar energy, and therefore these are the best machines available in the nature to convert solar energy into chemical energy that is stored in the form of glucose. Now, if you estimate the maximum efficiency of the photosynthetic apparatus of the plants, you find that only 26% of the input energy is converted into chemical energy. And that is the reason why the plants, they are happy to have their food made, but they cannot move about because this conversion is not efficient enough to give them extra energy to move about, to run, to fly. And that is the reason why we as a human beings would like to employ energy all around us to do much more useful work than just manufacture our food. And therefore, we have to harness energy with a much better efficiency. So once again, going back to where we can get the energy from, we can get the energy from wind. So these are windmills where the power of wind is used to convert into useful energy like electrical energy. This is a typhoon. This is one of the best manifestations of the energy that is contained within winds, which have formed a very highly concentrated zone of energy that is being carried by the wind. We would like to use the lightning, where a lot of electrical energy is being produced in the atmosphere, and if we could use this form of energy and charge our batteries for instance, we would also like to use the power of a plunging waterfall, where we can run the turbines in a hydroelectric project. Or it may so happen that we are going to burn coal and run the thermal power stations, or this is a lot more dangerous instance. One can use the heat energy that is being released when the molten lava flows out of a volcano, or maybe we can use the geothermal energies that are released when a geyser, a hot water geyser, erupts in the middle of an otherwise frozen landscape. So as you see that the source of energy is abundant, and we need to understand how to harness or take these energies from these sources and use them in a most efficient way to run our missions. Now, when I go further, then as you see that we have indeed been able to harness energy from certain sources. So it was long back when we made this observation that the steam coming out of the kettle can actually push the lid of the kettle up. So the steam is doing some work against the atmospheric pressure. And obviously the Industrial Revolution followed when we started having steam engines pulling the train carriages. And these days we have cars which are running very, very fast and with which we can cover a very large distance within a very short time. We are launching rockets where the motion of the rocket defies the forces of gravity using the rocket fuel. We can lift very heavy loads. For example, as you see, a very heavy load is being lifted by a crane, or it may so happen within our body, a load, a useful physiological load, a metabolite, can be carried from one place to the other by the use of biological motors like a motor protein that I have shown here. So the basic idea here once again is I will take energy from the abundant sources in nature and put them in action by converting this energy into useful work. Let me next explain the essential concepts that are crucial to the formulation of thermodynamics. First of all, we'll have to define a system, and essentially we'll have to talk about a system that is a macroscopic system. I will explain what a macroscopic system is, but before that, let me give you a summary of the questions that are posed in thermodynamics. So first of all, one asks, if you know your system of interest, then how do you define the equilibrium state of this system? And once you define the equilibrium state of the system, then experimentally, how do you prepare the system in the specified equilibrium state? So once you have prepared the system in an equilibrium state, the next question that you would ask is, if I want to induce the system to undergo a change in state, that is, I will perturb the system so that it passes from one equilibrium state to another, then the question is, how do we carry out this change in state? And then comes the all-important question of, during the change in state, I would like to harness energy, or in other words, I would like to make the system to do some useful work for me at the expense of its own energy. And then the question that comes immediately is that how do we maximize the amount of energy that the system will be using to do useful work. Now, with this basic framework in mind, let me take each of these topics or the concepts one by one and see how thermodynamics gives us a very general formulation to understand these concepts. So first of all, what we have is a system. So what is a system? A system is a part of the universe whose properties are being investigated. Therefore, if I look at this picture, what I will find is, you see there is a small green circle. This is representative of the system that we are interested in. We are interested in investigating the properties of this system. Then the system is located within a big blue box. This blue box is actually giving the surrounding to the system. So by definition, the surrounding is rest of the universe. So as far as our practical applications are concerned, we are interested in the system plus the surrounding, and these two make up the universe. Now, I have already mentioned we are interested in macroscopic systems in thermodynamics. So what do I mean by macroscopic systems? A macroscopic system is one which has macroscopic dimensions. So this means that if I am looking at the length scale, it would be typically 1 meter. If I look at the time scale in which the measurable properties are going to change, that is going to be typically 1 minute. And the number of particles, atoms or molecules which constitute such system would be very, very large, typically the Avogadro number, which is 6.023 into 10 to the power 23. Now, as you understand that this is a very large number of particles. Now, when I am talking about a macroscopic system, therefore, I am talking about some part of the universe where the length, height or the width is typically 1 meter, where there are Avogadro number of particles constituting this body, and therefore I should be able to see this system with my naked eyes. And then I say that if I am studying a system like this, thermodynamics focuses on the system in equilibrium, which means that all the measurable properties of this system will be independent of time. And this means that in thermodynamics, the essential dimensions that I use would include length and the number of particles, and there will be no concept of time. Actually, the name thermodynamics is a misnomer. It is now being replaced by thermal physics. Why? Because there is no dynamics in thermodynamics. We are interested in studying time-independent equilibrium properties of macroscopic systems in thermodynamics. And therefore, we understand that the essential concepts in thermodynamics are given in terms of the system, surrounding, and something else. As you see that my system, which is my green circle, and the surrounding, which is the rest of the blue box, they are separated by what is known as the wall. So what is a wall? Wall surrounds the system and differentiates it from the rest of the universe, which is constituted by the surroundings. And if I look at different examples of the systems that people talk about in thermodynamics, as you would see in the example cited here, they can be as varied as a complex machinery, or it can be a car engine, or it can be the engine of an aeroplane. We can also have macroscopic systems that we see these days, a laptop, a desktop computer, or a very large computing system or a supercomputer. We also see these solar panels these days, which are useful for the conversion of solar energy into other forms of energy. This is also a macroscopic system whose properties can be studied in terms of thermodynamics. And then, of course, we have the biological systems like the plants and an incredible machine of all, the human body. So as you see that thermodynamics actually covers a wide range of natural and man-made systems which we can see with our naked eyes, where the typical length, height or width measures in terms of meters or centimeters, and where if we ask you how many atoms or particles are there in a small part of this system, you would say that that has to be some multiple of the Avogadro number. So with these, we are facing this challenge in thermodynamics that we have to have a perfectly general description of the time-independent properties of all these macroscopic systems in a simplest possible way, such that we can employ some of them to do some useful work for us. And this is exactly what thermodynamics does. So thermodynamics does this incredible job of providing a simple general description of this wide variety of systems. And it says that there exist particular states called the equilibrium states of simple macroscopic systems that are characterized completely by 3 variables, and 3 variables only. As you understand, this is an incredible simplification because we are talking about systems comprised of 10 to the power of 23 particles. If I wanted to have a complete description of these 10 to the power of 23 particles, then I would have needed to solve 10 to the power of 23 multiplied by 3 coupled second order differential equations, and it is impossible to do so. Therefore, thermodynamics is telling us if you are interested to know the properties of the system independent of time at the macroscopic level, here is what you need to do. All you need to do to start with is choose 3 independent variables and specify the state of the system with it. So in the next lecture, we are going to look at different situations and how we can use different combinations of 3 independent variables to define the equilibrium state of a macroscopic system as prescribed by thermodynamics. Thank you.